Okay, let's look at parallel plate systems, or continue looking at parallel plate systems. I'm not sure exactly where we got to on the last little bit that we did, but what we want to do is we want to have a bit of an understanding of what goes on when you have two charged opposing plates. Okay, so we'll say they have these charges on them, and from last time we understand that the field within here is going to point off of positive and directly onto negative. Okay, you can help yourself understand that by just thinking about where the field would point if you were a positive test charge. Okay, so from left to right in this scenario. Okay, so what that means then is if we talk about the field in here, okay, the field strength, okay, field strength is uniform. Okay, so E is uniform within the plates. So it's a little bit different than when you have, say, a spherical, charged object. As you get closer, the field strength increases, and as you get farther away, it decreases. In the parallel plate system, right, you'll see these lines are always parallel to each other, indicating the field strength is the same. So, let's say that this field strength is, 1,000. What units would I be in for that? For field strength here. What does a field do to an object? Supplies a force, right? It's a force field. And an electric field supplies a force on charge, which is measured in coulombs. So 1,000 newtons per coulomb. What that means is if I put some given charge, if it's 1 coulomb, well, it'll feel 1,000 newtons towards the right. So that's what that means. No matter where I put it in here, even if it's sitting right on top of this plate, it's still 1,000 newtons per coulomb. Okay, are you with me? All right, let's also, just for interest's sake, say that we have a separation here of, we'll go with 1 meter, just for kicks. Okay, I want to think about something here for a minute. What if I don't change the amount of charge on here, but I open these plates up wider? What do you think would happen to the field strength? Would it stay the same, or would something happen to it? What do you think? If I were to make these plates farther apart, but I kept everything else the same amount of collected charge on each plate, but I moved them farther apart. Yeah. Well, interesting. Would it decrease at a square to distance? Where do you get decrease at a square to distance? Where does that happen? Right. If you're talking about 3D spherical space. Okay. So yeah, in 3D spherical space, as you get farther out, this shell that you're drawing, this expanding sphere, right, the area increases at a squared distance. So therefore, the field for a given area decreases at a squared distance. It's a geometrical relationship. Here, though, right, yeah, I mean, the space is 3D, but you're only increasing the distance in, I guess, one dimension, essentially, right? So no, it does not decrease at a square, but it does decrease linearly. Okay, and we'll explore that a little bit more. So that's a good thing to know. So what happens is, as I move this farther and farther, leaving this charge in there, it feels a less and less and less of a force. What happens if I move this to an infinite distance away? What happens to the force on this charge? Right, it approaches zero. So it's sort of like a limits type, situation. Will it ever be zero? Shouldn't be. But yeah, anyway. Okay, so electric field is uniform within the plate. So let's just forget about moving it back and forth and just talk about this particular scenario. Okay. So what if I grab this object and actually, let's say it's over here. Sorry, that makes more sense if it's positive. And I push it this way. Okay, so I'm pushing it this way. Do I have to do any work to make it move from here to here? Why? Good. So I'm supplying a force, and I'm supplying that force over a distance. Okay? So the question now is, if I have a 1,000 Newton per Coulomb field strength, and I move this object from one plate to the other, how much work have I done to move it? In this case, it's 1,000 newtons, right, worth of force to exactly counteract the force field, right? So if it's moving, I don't have to supply any more than that. So 1,000 newtons times a distance of 1 meter gives me 1,000 Newton meters. Well, what's a Newton meter the same as? 1,000 joules of work. Okay? So that's interesting. It took me 1,000 joules of work to move how much charge? 1 coulomb, right? So this is for 1 coulomb. So what does that mean then when I've moved it all the way over here? How much potential do I have? 1,000 joules for every coulomb. What's that the same as saying? Good. So what we've done here is we've taken a field strength and we've worked it back to what the potential must have been. Okay? So if it works in that direction, could it work backwards in the other direction? Do you think? Like if I were to tell you, let's try this. What if I told you that, let's give you some information. Let's say we have this here, and let's say this is 100 volts. Let's say that this is a 2-meter distance. Can you work out what the field strength must be within this from just that information? Can you? Should we try? So we want field strength, right? Which is independent of the particular amount of coulombs that you have, right? It's per coulomb. So yeah, essentially, yeah, you are figuring everything out in reference to what 1 coulomb would do, right? So what does 100 volts really mean if we break it down? What is that telling us? What's that? Well, 100 joules per coulomb, right? 100 joules per coulomb. Okay. So how did we define a joule again? How do we get a joule? A Newton meter, which we got from doing force, right? Times distance. So in other words, we have 100, whatever our force is, times whatever our distance is, coulomb. Are you with me so far? Perfect. So in this scenario then, what's the distance? Okay, so that's 2 meters. So we know it's per, every coulomb, for every single coulomb. What must the force be then to get 100? 50. So 50 newtons. So in other words, within this 2-meter space, right, what must the field strength be? 50, and what are the units? Newtons per coulomb. Good. So you've just figured out what the field strength is. Does that make sense? Now why don't I just give you the formulas to do it? Okay? That's the thinking behind it. Does it make sense? Okay? Let's talk about the actual formulas. So we could say then, here, let's talk about this. Okay, so electrical potential energy is equal to the electric force times the distance that we push it, right? So the electric force times the distance that we push it, okay? And we also know that electrical energy is going to be equal to the voltage times whatever amount of charge we have, right? We've looked at this already, right? It's either the electric field times distance, or going backwards, the number of volts times the charge. Both are equal to the same thing. So I think that we can probably do this, right? We can say Fe times D should be equal to V times Q. Okay? We're not quite done yet. Let's just revise or see what we're talking about. So this is the definition of work, right? Force times distance. Okay? And this is also a definition for work when we're talking about electrical systems. This is in joules per coulomb, and this is the number of coulombs, right? This is, of course, in newtons, and this is in terms of meters. So this is also work. So work equals work. Okay? Now let's just rearrange this. We should also be able to say that Fe over Q should be equal to V over D, right? Because that's just a rearrangement of this formula. Divide Q off, divide D off, and here we are. Fe over Q equals V over D. Now what are each of these, or what is this anyway, the definition for? Force per unit charge. Field strength. Aha! So we were able to find field strength with voltage and distance, like we did. And we were able to find field strength with knowing the electric force, right? And looking at how much that applies onto a coulomb of charge. So we've made an equivalency here, okay? This is kind of important. You might be given this scenario and asked to figure out what the field strength is, okay? Or you might be given the field strength and one other piece of information, and asked to find something else, right? If you're given distance, you might have to find voltage. If you're given, charge, you might have to find force, and so on. So this is an important, useful equivalency when you're dealing with this stuff, okay? So let's see if we can use it for something. Let's try a challenge problem, okay? So let's say a 120 volt potential is supplied to a parallel plate system I'm going to quickly draw that. Parallel plates are quite chunky here. Okay, so there it is. Charge built up on either side, and there's going to be a field in between here. That field will point in this direction, and it will be uniform. Okay. Let's say these plates are 10 centimeters apart. Job 1, find E. Okay, so find E in this scenario. And let's just remind ourselves that we've got 120 volts between these two plates. Okay, potential difference is 120 volts. So find E within there. So there's a couple of ways we can do it. Well, there's one probably proper way. So we learned just recently that E is equal to voltage divided by distance. So 120 volts divided by 0.10 meters. And what should we get for field strength from that? Good. And the units, of course, are volts per meter, which are the same as, well, volt is a joule coulomb, right, per meter. And then this is newtons times meters. So meters are going to cross. Oh, wait, sorry, that's not right. Oh, yeah, that is right. Or is it? Yeah, it is. Right, I did write it funny. And it ends up in newtons per coulomb, which is exactly what it should be. Right. Okay? So the volts per meter is the same as the Newton per Coulomb. Okay? I think I did my math right. Yeah, because I'm dividing by... right. Yes, I shouldn't have this. Because I put it underneath. That's right. That's the problem. I shouldn't have had that negative one there. I should have written it linearly. This is why we don't do it this way. Okay, anyway. Let's figure something else out. Okay? Number 2, an alpha particle is placed at the left plate. So at the positive plate. Okay? If released, calculate its velocity upon striking. The negative plate. How do we go about doing that? What do we need to know? Okay, we do need to know that, but let's generically write out what we're looking at here. What scenario are we dealing with here? We're dealing with, I'll give you a hint. This is an energy type problem. Good. So it's a potential energy being converted into a kinetic energy. So electric potential into kinetic. Right. So the things we need to know then, well, let's look at how these are going to shake out. So first of all, how do I figure out what my electrical energy is going to be here? How do I do that? What's that? This is electrical energy, not field strength now. Is it not? Is it not the potential times the charge? And what else does it say? What is it also equal to? Okay, just let me help you. Okay, you have 120 volts. What does 120 volts mean? Same plates. It's the same question. Just continuing. Okay, sorry, Hannah. Part B, there. Okay, so if you think about this in terms of joules per coulomb, well, then we want to know how many coulombs there are in an alpha particle, right? Q of an alpha particle. And we want to say all of that charge, since in our magical world none is ever lost, all is being converted into kinetic energy. How do I define kinetic energy? Good. 1/2 m squared. Excellent. So what are our unknowns here right now? Well, one unknown is a mass, but we should be able to figure that out because what's an alpha particle made of? Helium nucleus. Right. So 2 N's and 2 P's. So in other words, it's the same as 4 atomic mass units. Okay? So 4 AMUs. Okay? What we want to know at the end of the day is we want to know velocity. Okay? What's the charge on an alpha particle? It's got how many protons in it? It's a helium nucleus. 2 protons. So it's got a charge of plus 2 elementary charges. Right? Okay. If we want to solve for V here, we're going to multiply this side by 2. Right? We're going to divide this side by mass. We're going to root the whole thing. So let's rewrite it. V, the velocity now, not the voltage. V should be equal to 2 times the electric potential energy, okay, which is 120, times Q, the charge on an alpha particle, all divided by the mass. Okay? So let's start to fill this in. 2 times 120 volts. Now what is the actual value in coulombs of the elementary charge? You have 2 of those. Can someone look it up? What's the elementary charge? Or do you know it off the top of your head? What's Coulomb's constant? 9 times 10 to the 9, right? Which means that there's 9 times 10 to the 9 elementary charges in a Coulomb. So it would be the inverse of that, right? 1 divided by 9 times 10 to the 9, which should be what? 1.6 times 10 to the negative 19 coulombs, and we have 2 of those, right? There's 2 of them in there, okay? And then we need to know the mass of an alpha particle. Ooh, sorry, should be 19. 1.6 times 10 to the negative 19 coulombs, right? Each of those protons carries that amount of charge, and there's 2 of them. And then the mass of the alpha particle. I'm going to draw an alpha particle away, find me its mass. Anybody? So it's 4 times what value? Okay, so that's roughly the mass of a nucleon. Okay, so for a prize, who can do the math the quickest? Okay, most of us in the room got 1.1 times 10 to the 5. Although a few got a different answer, I think we're gonna go with this one. Assuming we did our math correctly on our calculators. That is not math many of us can do in our head. Anyway,